Go ahead, yes, sir.
Okay, so today I'm going to be talking about developing novel EGFR inhibitors to overcome the drug resistance of recurring drug Dacomitinib on the double mutant C797S L787R through virtual screening and kinase inhibition assay, which is probably familiar to some of you because we kind of did this in wet lab, which is exciting. So for some background, EGFR stands for epidermal growth factor receptor. Mutations of the EGFR gene are often found in non-small cell lung cancer, which is specifically what I was looking at. These mutated genes are responsive to tyrosine kinase inhibitors, which block the hyperactivity of the EGFR. And I am looking at the double mutation C797S L787R, because it has gained resistance to drugs. And the one we did in wet lab actually had the C797S mutation, so that's a common one, I guess, that's found in the EGFR gene. So kind of the process, first this is basically just what we did in dry lab. This semester, you start with the drug library and the 3D structure that was already found by the bioinformatics student, and you just plug that in. Then you do the glide docking to kind of figure out where the binding will occur, diversify the structure, find, the different angles in the way that it will bind, find a hit compound, decide which ones are the top matches to binding to hopefully inhibit the growth. And then the kinase assay, the synthetic pathway analysis, and then the substitution site analysis are all kind of what we did towards the end in terms of, in wet lab, we kind of did the assay part, and then dry lab with the pathway analysis, kind of determining how it binds. That was like the docking site and everything. And determining from there the docking scores, the IC50s, and so on. So the methods, the first step was to create the mutant and the wild type on Maestro, then test the list of FDA drugs against it. This took a long time to load. So the top 5 mutants, or the top 5 drugs that matched, all had docking scores of the highest was negative 11.627, which was Dacomitinib, which is kind of similar to the one that we used in wet lab. It ended with the INIB, so they're definitely in the same family. But all of the other docking scores of the other top matches were in the -10 or -9, so pretty similar. The wild type IC50 was found to be 6, and I did not find the mutant IC50 anywhere, so I'm not sure what that is. But Dacomitinib was the top match, and in the picture there you can see the drug bound. The drug is in the red, and it's bound to the EGFR, which is the purple. So the expected results based on the experiment, which would basically be identical to what we did in wet lab, considering it's literally the same exact thing, except for a slight change in the mutation. The wild type, you want to find the IC50 in comparison to the drug for the wild type to be higher, because you want the wild type to not be affected by the drug when it's bound, but the mutant, you want the IC50 to be lower, so it does bind correctly and it does affect the mutant growth, so growth is inhibited to kind of stop the cancer from expanding. So these results would indicate that the mutant would be suppressed to decrease the cancer growth, and it would not affect the wild type because that would cause harm. And this is just my references.
It's a question, actually.
Oh, you're gonna ask that one. Okay. Hold on.
Could you go back to what type of cancer involved?
Yeah, it's non-small cell lung cancer, just a type of lung cancer.
Is it rare?
Not that I think so. There was a lot of research on EGFR, obviously, so I'm pretty sure it's pretty common in terms of, yeah.
Very common. The ability part that most common Okay, so my time. We go to methods. The previous slide that had the one.
This one?
So here you can improve a little bit by, okay, so the first step, glide docking, really is assign the docking score for each compound from the drug library, right?
Mhm.
And then we're ranking that about the top compounds. And then for top 100 or top kind of the 100 compounds, then we do the clustering that give us a different more like scaffold. So then we pick the heat that picks the 5 kind of different more like scaffold, and then do wet lab testing. So the next 2 steps actually is a different way. So synthetic pathway analysis is basically try to, if have initial heat, typical is not good enough to be a drug. Then you want to modify it, right? Modify it and resynthesize the analog and retesting analog to optimize that the compounds. Typical for the drug, you need to do cell generation optimization. So that synthetic pathway analysis, try to figure out how to synthesize that compound. Once you figure out how to synthesize that compound, you induce the R group. And then you can generate it. That's the substitution side analysis. Then you allow you to generate a set of the new analog. And then we can do the virtual screening again. Through the virtual screening, we can find the analog which has exactly the substitution site and also has some synthetic pathway information processed to the medicinal chemist. And then the chemist you can synthesize, came out new compound to testing. Actually, in my lab, we did this one for a compound identified by Dr. Cap. And we did exactly the synthetic pathway analysis on fusion. And then we generate a library of 1,000 compounds, which are actually virtual compounds, not synthesized. And then we identify the top 5 for each category. We pass that information to them. Actually, the medicinal chemists actually synthesize some of them and test it. You know what? It worked. So this paper now is under review in the journals, actually. And you show, this is exactly showing the application we have on to optimize that. Okay, so yeah, that's good. So that's kind of workflow. So it's synthetic, that is not, it's more about how to optimize the next generation of the, okay, so next slide. So here, if you have the docking score, you want to indicate that's wild type or on the mutant. If you have the both, then that's good because you know the difference in the docking score basically can tell us is the resistance or not resistance. So if you can provide that information, that'd be good.
Okay.
And we know that this drug has drug resistance, so you should expect the docking score, ideally, if correct, should be not as good as the on the wild type, right? So then you can discount that one.
Okay.
Yeah, that's it. Good.
Thank you.